Let's start simple. Suppose that we know x is going to infinity. Here's such a list up here, or I'm writing the same list using powers of 10. This shouldn't catch you too much by surprise. If x is going to infinity, what's x squared going to go to? Well, I don't really need to go much further. Infinity. X cubed is going to be going to infinity even faster. That wasn't so bad. So now if x approaches minus infinity, here's a similar sort of list. What does x squared approach? I'm already tired of counting zeros, so we'll notice that x squared should be approaching positive infinity. X cubed can be seen to be approaching minus infinity. The zeros are really getting out of hand over here, but every term is negative, so it has to be negative infinity. And in fact, after that, I think it's fairly clear that x to the fourth, because all of the fourth powers are positive, those are going to positive infinity. Things like x to the fifth, because of the odd power, go to minus infinity, and so forth. All right, now things start to get a little bit more interesting. We have our x going to infinity, and then the question here is, what does this expression with the cubes and the squares in it, etc., what does that go to? Look at how they're put together. Essentially, we have this part going to plus infinity. At the same time, what's over here is going to negative infinity. They're fighting with one another. Which one's going to win? And I'm claiming that the x cubed term is going to win easily. Let's look over here at what sort of things come out of the formula. If I plug in the 1, you get the 1 minus 6 minus 4 minus 8. That gives you negative 16. And already, when I start plugging in something like 10, when I do the subtractions, I'm going to get something that's positive. I decided that I was going to look a little bit more closely once we got to 10 squared. When I plug 10 squared in over here, there's what it looks like. That's a 10 to the 6th. It's a 5 times 10 to the 4th, a minus 4 times 10 squared. So you'll notice that that 10 to the 6th is going to, the million, is easily going to overwhelm what's over here, which doesn't involve anything any bigger than a multiple of 10,000. All right, we just noticed that the limit of x cubed minus all this stuff up here, that's going to be plus infinity. Similarly, the limit as x goes to minus infinity of the x cubed expression here is going to go to minus infinity. If we think about what this means for the graph of that function given in the formula, this is saying that if we look to the far right, that the graph is going up and up and up toward plus infinity, whereas saying that the limit to the left is going to be minus infinity is telling us that the graph is going down. So the limit information over here is telling us about what the textbook calls the end behavior of the graph of our function. It's telling us about what's happening to the far right or to the far left on that graph. Here's another example that can be dealt with in a similar fashion. The formula that I was looking at over here involves an x to the fourth minus smaller powers. In this situation, because the x to the fourth wins, the limit as x approaches infinity of f of x is going to be positive infinity, and the limit as x approaches minus infinity of f of x is going to be plus infinity, which is another way of saying that the graph of this function goes upwards on both ends. To analyze the graph of something like an x to the fifth minus smaller powers, remember that we know what the limits as x approaches infinity or minus infinity are for x to the fifth. The limit to the right is plus infinity. The limit to the left is negative infinity. This is telling us that the graph is going up to the right and down to the left. If that x to the fifth term was replaced by a negative multiple of x to the fifth, that term still wins. However, the infinite limits are going to be switched in sign from what they were before, which would be saying that if you look at the graph, that instead of going up on the right, it's going down, and instead of going down on the left, it's going up. What I'm observing here might already be clear, but let's run through it quickly anyway. If I have an x approaches infinity list, like for instance that one, the corresponding 1 over x list, in this case, looks like this, and pretty clearly in all such cases, 1 over x should be going to 0. Similarly, the x squared list would be going to infinity, So that would mean the 1 over x squared list would be going to 0. And in fact, in general, if p is your favorite positive number, the x to the p list would act like the x squared list, and they would go to infinity. And as a consequence, the 1 over x to the p list would be going to 0. That as x goes to infinity, the corresponding 1 over x to the p's go to 0 is what I'm hoping seems to be an obvious fact, and this can be used to find limits as x goes to infinity of various kinds of functions made from fractions. So let's look at an example. Okay, so let's try to find the limit as x goes to infinity of this fraction that involves polynomials. In other words, it's a rational function. I'm going to take that expression and move it over here, and then I'm trying to be careful with the algebra. I'm going to multiply it by another fraction formed by 1 over x cubed divided by 1 over x cubed. The x cubed came into play because I noticed that the biggest power of x that appeared anywhere in the original fraction was x cubed. Now, when I multiply through doing the algebra to go to the next step here, I have x times 1 over x cubed times 1 over x cubed, and those sorts of things popping up here, a lot of which will simplify significantly. For example, the x over x cubed would simplify into a 1 over x squared, and so forth. Now, looking at what I've got, as x goes to infinity, this part is going to go to 0, and this part down here is going to go to 0. In the end, as x goes to infinity, these numbers up here are going to settle out to being a 0 minus 1 divided by 2 plus 0. I can simplify. There's our final answer. I should point out that in the example that we just looked at, looking at the polynomials in our fraction, the biggest power of x in the numerator is the same as the biggest power of x in the denominator. You'll want to recognize this sort of situation, as they will tend to lead to a nice answer. This example is very similar to the last one, except you'll notice that if we look a little bit more closely at the fraction, that the biggest power of x is an x to the fourth, and it appears in the numerator and not in the denominator. I'm going to key on the biggest power in the denominator and use that over here when I multiply through both numerator and denominator. After simplifying, I get something like this. Looking at the limit as x goes to minus infinity, the 1 over x and the 1 over x squared, they're going to each be going to 0. So I can substitute in and simplify. The resulting expression looks like a minus 1/2 times x. In this situation, the x is going towards minus infinity. Each of those numbers going toward minus infinity is multiplied by negative. So in the end, the resulting limit is going to be plus infinity. Here's another example. This time the power of x in the denominator is the biggest one. It is still an x cubed that is the biggest power in the denominator, so I'm going to use that to multiply through as before and look at how everything simplifies down. Notice that this result is going to leave all zeros in the numerator, and 0 divided by whatever is perfectly nice, and in fact is my favorite number. One more quick example. I want to take the limit as x goes to infinity of the square root of one of these sorts of fractions that we've been looking at. I can get this done by just inserting the algebra all inside of the square root, multiplying through, doing the things that we've been doing to see that what the limit value inside should be. Because square roots are a continuous sort of operation, we in fact can just take the square root of that inner result, and I'm perfectly happy leaving a square root of 2 in the denominator here. There's no particular point in rationalizing denominators if it makes the expression more complicated rather than simpler. I should warn you that when finding limits as x goes to infinity, if I tell you to use what I'm calling the 1 over x to the p trick, then you should know what I mean and then be able to carry out the algebra appropriately to work things out using that method, rather than some other method that might give you the right answer but doesn't make the inner workings of things as clear.